You've likely seen many images and videos showing the planets of the solar system orbiting the Sun. However, not only do Earth and other planets orbit the Sun, but the Sun itself is also in motion. The Sun, and with it our entire solar system, revolves around the center of our Milky Way galaxy at a speed of approximately 230 kilometers per second. This movement is far more complex than we initially assume. Let's start with how we typically visualize planetary orbits. In most depictions, planets orbit a stationary sundial. In reality, however, the planets exert a gravitational pull on the Sun, just as the Sun pulls on them, causing the Sun to move. Astrophysicists state that within the solar system, there exists a barycenter, the center of mass. This is a real point around which all bodies in the solar system orbit. Relative to this barycenter, the Sun performs a complex pirouette in response to the gravitational pull of Jupiter and Saturn. Sometimes this barycenter lies within the Sun's surface. However, when these two gas giants align, the barycenter can lie outside the Sun. How does this affect Earth's orbit? The barycenter's movement is slower than Earth's orbital velocity. This causes Earth's elliptical orbit to slightly elongate and contract over the orbital periods of Jupiter and Saturn. This effect, while subtle, is measurable and has been confirmed by precise astronomical observations. The influence of Jupiter's and Saturn's gravity on the Sun's position affects the Earth's orbit, slightly changing the timing of seasons over long periods of time. The slight wobble in Earth's orbit is a very small effect and does not affect weather patterns on short timescales, but it could be significant on timescales of thousands of years. Earth's motion within the solar system is complex, but far less so than its galactic movement. The solar system contains relatively few bodies whose gravitational influence is significant, with our star's gravity overwhelmingly dominant. The gravitational field of our galaxy is different. At its center dominates the supermassive black hole Sagittarius A, while nebulae and stars create their own gravitational fields. By tracking the movement of these components, we can learn more about our galaxy. For example, astrophysicists have determined that our solar system moves at approximately 230 kilometers per second relative to the center of the Milky Way. This means a complete orbit around the galactic center takes roughly 230 to 250 million years. The last time Earth was on the opposite side of the galaxy, the trilobites were extinct, while gorgonopsids had just begun to populate Pangea. The precise timing of these events are still being studied by geologists. To describe the Sun's galactic motion, we need a reference point. While the galactic center seems a logical choice, it's challenging due to the Sun's non-circular orbit. Researchers have found that nearly every star in the Milky Way begins its life with a near-perfectly circular orbit. This is because the gas and dust clouds from which stars form are forced into circular orbits due to friction. After a star forms on the same orbit as its parent cloud, it gradually deviates due to gravitational interactions with other Milky Way objects. Therefore, to determine the Sun's speed, we need to find young stars still on their original orbits and average their movement relative to our own. These observations are made using high-precision astrometry, measuring the tiny shifts in stellar positions over long periods. From these measurements, astrophysicists have discovered that the Sun moves slightly faster than expected for a circular orbit. Calculations show it drifts forward at about 5 kilometers per second, inward toward the galactic center at roughly 8 kilometers per second, and upward from the galactic disk at 7 kilometers per second. This peculiar motion significantly impacts the solar system's galactic path. The slow drift toward the galactic center doesn't mean Sagittarius A is pulling us in. The Sun is attempting a slightly elliptical orbit around the galactic center and is currently approaching it. However, the Milky Way's mass is distributed throughout the galaxy, unlike in the solar system. This makes simple elliptical orbits impossible. Instead, the Sun's path follows multiple orbits simultaneously, creating an epicyclic galactic motion. Our upward velocity away from the galactic disk of about 7 kilometers per second is also notable. We are currently several tens of light years above the midpoint, though precisely defining the galactic disk's midpoint is difficult. However, there is more matter below than above us, and the disk's gravity slows our upward movement, preventing our escape. In a few million years, we'll rise roughly 300 light-years above the galactic disk, then our upward motion will slow to a stop, after which we'll begin to fall back. The Sun makes one such oscillation approximately every 60 million years. These vertical oscillations of the Sun are not just an interesting phenomenon. Some astronomers believe they could be directly linked to the 5 major mass extinction events in Earth's history. The timing of these events are still actively researched, but it is likely that other factors also play a major role. The center of our galaxy's disk is a hazardous place for the solar system due to the higher stellar density. This increases our risk of nearby supernovae or collisions with other objects that could destabilize the Oort cloud, potentially sending a barrage of asteroids and comets toward Earth. The motion of the Sun and other stars is a valuable scientific tool, allowing us to test various theories about mysterious, invisible dark matter, whose existence was initially inferred from its strong gravitational influence. Numerous theories exist about dark matter's composition, each making different predictions about its self-interaction. However, the vertical oscillations of stars provide observational evidence for the existence of dark matter. This gravitational interaction is studied by analyzing the movement of stars both within and outside of the galactic plane. We now understand the Sun's galactic motion. But what about the solar system as a whole? The plane of Earth's orbit is inclined at approximately 60 degrees to the galactic plane. This leads to the appearance of a flattened disk as the planets move through the galaxy. Planetary orbits cause them to spend half the year ahead of the Sun in its galactic orbit and half behind. For Earth, the maximum lead occurs in September and the maximum lag in March. For half the year, Earth moves in the same direction as the Sun through the galaxy, with their speeds adding up, reaching maximum velocity in June. During the other half of the year, we move backward relative to the Sun's motion. Therefore, Earth's galactic motion is slowest in December. Currently, the ecliptic is nearly aligned with our Sun's orbital motion. However, due to the conservation of angular momentum, the solar system's plane will not rotate with the Sun's orbit. In about a quarter of a galactic orbit, the ecliptic plane will be edge-on, making the solar system resemble a giant wheel. Now we have a picture of the solar system's movement through the galaxy. But how are we moving through the universe? The Milky Way is pulled by the gravitational fields of the local group of galaxies. We're hurtling toward the Andromeda galaxy. The local group, Andromeda, the Milky Way, and other smaller galaxies, is being pulled towards the mysterious Great Attractor. Defining a reference point to determine our relative speed is challenging, except for the reference frame provided by the universe's various epochs, the cosmic microwave background. The CMB is faint radio wave light emitted by the hot hydrogen that filled the universe before the first stars formed. Hydrogen atoms were moving in all directions, but with an average velocity. If you were there at the beginning and moved at the average speed of those atoms, the light produced by the atoms would appear uniform in all directions. However, if you had a different velocity, the light approaching you from the front would appear slightly